we're going to talk about rational functions now, which rational functions are functions that are written as fractions. So an example would be like f of x equals 1 over x. That's a rational function because it's a fraction. You can't really write it as something other than a fraction. I mean, you kind of can, but like in essence, it matters that there's an x on the bottom. That's what makes this graph look special. What it actually looks like if you graph it is it's got a couple of key things that aren't there in like parabolas and other graphs of just normal polynomials. It has a vertical asymptote, which is a vertical line that our graph never touches. It has a horizontal asymptote. That word asymptote means it is referring to, in mathematics, a line that your graph gets close to and approaches but never actually crosses. And then the graph itself is up here and like curves towards the asymptotes either direction. The same thing happens down here. And if you have a calculator and can plug in 1 over x to it, you'll see that it should look something like this. So when we want to figure out what's special about rational functions, that's two of the things that are going to matter, horizontal and vertical asymptotes. Another thing that can happen is sometimes our graphs have holes in them. And then the last thing that we care about is typically our x-intercepts, which isn't written on here. That should really I guess be a step down here at the bottom, which I'll add in a second. But and we can also talk about the domain of our function. So domain is something that a lot of students find really tricky, and it has to do with if I look at my graph from left to right, and if I follow my graph from left to right, what x values will my graph have, and what x values will they not have? So the only x value that this graph that I've drawn as an example, the only x value it won't ever have is this one right here where my asymptote is x equals 0. And that's because of the idea that the only way I can get an error with this equation is if I try to put a 0 on the bottom of my fraction. Because you can't divide by 0. It's something that doesn't make sense to try to do because of the way division works. And so we didn't talk about the domain of our function. So, and then step 6 on here, if you're reading through these steps, they may not make a whole lot of sense right now, but once we start actually talking about them, they will. So hang on. Set the top equal to 0 for your x-intercepts. So the first thing we want to do when we look at an equation, and so we're going to do an example like this, 2 over x squared plus 3x. And we're going to find all of these things, our horizontal asymptote, the holes in our graph, our vertical asymptote, our x-intercepts, and our domain. And so when we do this, there's a process we can go through that kind of makes this the easiest in my opinion. And so the first step is that we want to find the horizontal asymptote. And horizontal asymptotes are tricky because there's like 3 cases that have to that we're like trying to find the difference between. Basically, we compare the x's on top and bottom, and so we only care about the biggest exponent, the x with the biggest exponent and on top, and the x with the biggest exponent on bottom. If there's a bigger exponent on top, that means there's no horizontal asymptote. If the bigger exponent is on bottom, it means our horizontal asymptote is at y equals 0. And having the same exponent means that we're going to take the numbers in front of our x's and make a fraction. So what I want to do on this is I want to say, well, there's not any x's on top, but there's an x squared on bottom. So there's a higher exponent on bottom because there's not one on top. This would be like an x to the 0 up here. And so 0 is smaller than 2. So I like to call this kind of graph bottom heavy because the x's on the bottom outweigh the fact that there's not an x on top. And so because this is bottom heavy, that means that our horizontal asymptote is a line y equals 0. Then once we've figured out our horizontal asymptote, our next step is to factor the top and the bottom as much as possible, and that's going to help us find almost all of the rest of the things on our list. And so whenever we factor the top is just 2. Like, there's nothing we can do to that 2. But on bottom, since there's 2 terms, we can say, well, these both have an x. Let me take out the x and write x times x plus 3. So once we've factored, there's things that the top tells us and there's things that the bottom tells us. But to figure out the wholes only happen if something cancels. So if there was an x on top here next to the 2, the x's would cancel and that would create a hole. Or if there was an x plus 3 on top, they would cancel and it'd create a hole. Since nothing cancels, we would say that there aren't any holes. Next comes our vertical asymptote. And so step 3, if something cancels, set that equal to 0, this is a hole. So we didn't have anything. So step 4, of what doesn't cancel, on the bottom, it's your vertical asymptote. Oh, I did put the thing about x-intercepts. We don't need that last step. Wow. So on step 4, after you've canceled stuff out, whatever's on bottom is your vertical asymptote or asymptotes. The top is your x-intercepts, which are also called zeros. So on the bottom here, we set these things equal to 0 and we solve. So we get x equals 0 and we get x plus 3 equals 0, which means x equals 0 and x equals -3. Those things on the bottom that haven't canceled out with anything are vertical asymptotes. So we have one at 0 and one at -3. On top, we set the top equal to 0 and solve, and that gives us our x-intercepts. Now this is a weird situation when I have a number equals 0 because 2 does not equal 0. Even if it did, there's not an x to solve for. When that happens, when you have a number equals 0, that means there's not an x-intercept. So this would be none. Now our domain is made up of us we're trying to list all the things from negative infinity to positive infinity that we can use for x values. But the problem is that there's 2 things that if we try to plug into this equation up here that don't give us answers, that would give us errors on our calculator. That's at 0 and -3. So our domain we write by saying, well, I can go from negative infinity to the first of these 2 numbers. The one that's farther left goes first, so that's -3. And then I can go from -3 to 0. And then I can go from 0 to infinity. And so what this does, the fact that these are parentheses with these numbers around it, it's telling us that we're going to skip over -3 and we're going to skip over 0. And every other number besides those 2 numbers are a part of our domain. But that's called interval notation. That's mathematically how we can write that. So let's try this on a couple more problems, just figuring out all these different things. So step 1, we are going to find our horizontal asymptote by comparing the x's on tops with the x's on bottom. So I only care about the biggest exponent on top, the biggest exponent on bottom. X squared and x. X squared has more x's than x does. So this is top heavy. And so a top heavy graph doesn't have a horizontal asymptote at all. And so that's what we're going to write is no or none. There's not a horizontal asymptote. Now, just an FYI, depending on what math class you're in, you might end up going farther with that and saying, well, if there's not a horizontal asymptote, there's actually another kind of asymptote called a slant asymptote. And that can be something that happens. Anyway, now what we want to do is we want to factor so that we can see if anything cancels out. Because if something cancels, that makes a hole in our graph, and we need to know that. So x squared minus 4, since it's a minus sign and I can square root 4, splits up into x plus 2 and x minus 2. On the bottom, we've got 2 terms, and so they both have something in common that we can take out. I'm going to take out a -5, and that leaves me with x plus 2, because if I take a -5 out of -10, it gives me a positive 2. So something does cancel here. The x plus 2's cancel, and so where we have something that cancels is a hole, but what we have to do is set it equal to 0, where x plus 2 equals 0 is that x equals -2. And that is where our hole in our graph is that x equals -2. And since it's canceled, we're going to ignore that for the rest of this problem. So for instance, our vertical asymptote is where the bottom equals 0. Well, the x plus 2 is not there anymore because we took it out because it's a whole. All we can do is try to set negative 5 equal to 0. Negative 5 can't equal 0 though, so there's not a vertical asymptote at all on this one. Our x-intercept comes from where the top equals 0. And again, we're not going to worry about the x plus 2 part of that because that we canceled out. Just the x minus 2 equals 0 is what we care about. And so that is positive 2. That's where our x-intercept is. Our domain is going to come from all the things that are on bottom that we got. And so it comes from our holes and our vertical asymptotes. And so all I have is negative 2 for that. So I'm going to go negative infinity, comma, negative 2, and then negative 2, comma, infinity. And that's all of my pieces on this one. So one more. We need the horizontal asymptote. And so there's a squared on top and a squared on bottom. And since those are the same, what we do is we take the numbers from in front of our x squareds. And so since there's not a number in front of the x squared on top, that's a 1. The number that's on bottom is a negative 4. If I put those together as a fraction with the top over the bottom, that's negative 1/4 is our horizontal asymptote. So whenever they're even like that, they both have an x squared, you just take the numbers from in front. Now I need to factor. So on top, they have an x in common. So I take the x out. And then on bottom, this is actually going to take a couple steps. So they all have a negative 4 in common that I can take out. So I'm going to do that first because that makes, well, otherwise it'll be really hard to factor this, and I'll probably factor it incorrectly if I don't take the negative 4 out first. Once I take out the negative 4, then I'm going to split this into 2 more parentheses and say what multiplies to get 3 and adds to get 4, which is just 3 and 1. So this is negative 4 times x plus 3 times x plus 1. So the x plus 3's cancel, which gives me a whole at x plus 3. So I set x plus 3 equal to 0, and I solve that and get a negative 3. That's my whole in this graph. What's left on bottom, which is the x plus 1, I set equal to 0 and solve, so my vertical asymptote is x equals negative 1. What's left on top I set equal to 0, which is this x, and so if you set x equal to 0, it doesn't actually need to be solved because it's already solved. My x-intercept is at x equals 0. The domain comes from these two combined, and so I have negative 3 and negative 1, which is negative infinity, comma, negative 3, comma, negative 1, and then negative 1, comma, infinity. And that's all there is to it. And so it really just takes some practice and, you know, maybe memorizing those steps, especially the first one with the horizontal asymptotes. There's also ways that if we plug these into our calculator that we can look at the graph and have the graph help us figure it out. But the more you know about how the equation works, the easier it is to tell what the graph is telling you. So it's kind of a catch-22 that looking at the graph will only get you so far if you don't understand the math behind it, but looking at the math behind it only gets you so far if you don't have all of it, memorized, or you don't have a good understanding of what's happening. So that's the idea of rational functions, and then in another video we'll talk about actually putting this onto a graph and graphing rational functions.